Welcome back to the channel, my fellow curious minds. Have you ever stood on a balcony, accidentally knocked over your coffee mug, and watched it tragically plummet to its demise? We experience gravity every single second of our lives. It is the invisible glue keeping us tethered to this spinning rock. But here's the thing. Gravity is secretly tricking you. Imagine you are standing in your living room, holding a solid, heavy steel hammer in your right hand, and a single, delicate pigeon feather in your left. If you open your hands and let go of them at the exact same time, which one hits the ground first? It is the hammer, obviously. Boom! It smashes into the floor, while the feather gently dances, flutters, and drifts its way down. It feels like the most obvious thing in the world. Heavy things fall faster than light things. Your brain, your intuition, and your everyday experience all scream that this is an absolute, undeniable fact of nature. But what if I told you that your common sense is completely wrong? What if the universe is playing a magnificent trick on your eyes? Today, we are going to strip away an invisible illusion that surrounds us every day, and we are going to drop that hammer and feather in a perfect vacuum. Get ready, because we are about to break reality. So, why did the hammer win that living room race in our first scenario? To understand the trick the universe is playing on us, we have to talk about the invisible, heavy soup we are swimming in right now, the atmosphere. When objects fall on Earth, they are not just moving through empty space. They are physically crashing into trillions and trillions of microscopic air molecules. We call this air resistance, or drag. Think of it like trying to run through a swimming pool. The water pushes back against your body, slowing you down. Air does the exact same thing to falling objects. The hammer is heavy, dense, and streamlined enough that it basically punches right through that invisible wall of air with ease. The feather, however, is a masterpiece of biological engineering, designed specifically to catch the air. It has a huge surface area compared to its tiny weight. So, as it falls, the air molecules push back up against it hard, slowing its descent into a graceful, lingering glide. Long before we could build giant vacuum chambers, a brilliant scientist named Galileo Galilei figured this out using pure logic. Legend has it he dropped balls of different weights off the Leaning Tower of Pisa to prove they hit the ground simultaneously. While that specific story might be a historical exaggeration, his reasoning was absolutely flawless. He realized that the only thing messing up gravity's perfect mathematical rule on Earth was the air itself. But what happens if we cheat? What happens if we suck every single molecule of air out of the room, creating a perfect vacuum? In 1971, during the Apollo 15 mission, astronaut David Scott did exactly this. But he did not need to build a vacuum chamber. He just used the moon. The moon has virtually no atmosphere. Standing on the dusty lunar surface, in front of a live television camera, Scott held out a solid geologic hammer and a lightweight falcon feather. He dropped them. And in one of the most beautifully poetic moments in the history of science, the hammer and the feather fell side by side, perfectly in sync, hitting the lunar dirt at the exact same fraction of a second. To understand why this happens, we have to look at the elegant, surprisingly simple truth about how gravity actually works. And it all comes down to a cosmic tug-of-war between two properties of matter: weight and inertia. Most people think that gravity pulls harder on heavy things, which makes them fall faster. Half of that sentence is completely true. The Earth absolutely does pull harder on the hammer than it does on the feather. The gravitational force acting on the massive hammer is indeed much stronger. But here's the brilliant plot twist. Massive objects are also incredibly stubborn. In physics, we call this stubbornness inertia. Inertia is an object's natural resistance to any change in its motion. A heavy boulder is really hard to push, right? It wants to stay still. A tiny pebble, however, is incredibly easy to push. The hammer has a lot of mass, so the Earth is pulling on it with a massive amount of force. But because it has a lot of mass, it is also highly resistant to being moved. The feather has very little mass, so the Earth only pulls on it with a tiny amount of force. However, because it has so little mass, it takes almost zero effort from gravity to get it moving. These two effects, the strength of the gravitational pull and the stubbornness of the object's mass, cancel each other out perfectly, mathematically, flawlessly, beautifully. Because they cancel out, gravity accelerates every single object in the universe at the exact same rate. On Earth, that acceleration rate is roughly 9.8 meters per second squared. Gravity is not a force that discriminates by weight or size. In the pure, silent emptiness of a vacuum, gravity is the ultimate equalizer. Let us take this simple truth, that everything falls at the exact same rate in a vacuum, and push it to the absolute limits of the universe. What if we are not dropping a hammer and a feather? What if we are dropping an entire planet and a single speck of cosmic dust? Imagine a supermassive black hole lurking in the dark center of a distant galaxy. Now, imagine we place a massive gas giant planet, something much larger than our Jupiter, and a tiny, icy comet at the exact same distance from this gravitational monster. If they begin from a standstill, with no other forces acting upon them, which one gets swallowed by the black hole first? Just like the hammer and the feather on the moon, the giant planet and the tiny comet will fall toward the black hole at the exact same rate. They will plunge across the event horizon, perfectly, side by side. Why? Because Albert Einstein took the simple realization of Galileo and elevated it into a scientific masterpiece, the general theory of relativity. Einstein realized that gravity is not just a standard invisible tether pulling things together like a magnet. Gravity is the actual geometry of the universe itself. Imagine the universe as a giant, stretched-out trampoline. If you place a heavy bowling ball, representing a star, a planet, or a black hole, in the center, it heavily warps and bends the fabric of the trampoline downward. Now, if you roll a small marble across that trampoline, its path will curve as it enters the deep dip created by the bowling ball. The marble is not being pulled by a mysterious magnetic force. It is simply following the natural curvature of the fabric. In our universe, that fabric is the four-dimensional grid of space and time, known as space-time. Massive objects warp the space-time around them. When the hammer, the feather, the comet, or the planet falls, they are all just sliding down the exact same invisible curve in the fabric of the universe. The curve is identical for everyone. Space does not care how heavy you are or what you are made of. It only dictates the shape of the cosmic slide you have to travel down. This mind-bending reality is exactly why the International Space Station and the astronauts floating gracefully inside it experience what we call weightlessness. A massive misconception among the general public is that there is zero gravity in low Earth orbit. That is completely false. At the altitude of the space station, Earth's gravity is still incredibly strong, almost 90% as strong as it is right here on the ground. So why are the astronauts floating? Because they are in a state of permanent, continuous freefall. The space station is moving sideways so incredibly fast, at roughly 28,000 kilometers per hour, that as it falls toward the Earth, the spherical surface of the Earth literally curves away beneath it. The station is constantly falling, but continuously missing the ground. And because the massive metal space station and the human astronauts inside it are all falling at the exact same rate, just like our hammer and feather in a vacuum chamber, the astronauts appear to float seamlessly. From the quiet, dusty surface of the moon to the chaotic orbits of stars circling the supermassive black holes of the cosmos, this fundamental rule holds the architecture of the universe together. Whether you are a microscopic particle drifting through the interstellar void, a massive asteroid plunging toward prehistoric Earth millions of years ago, or a blazing star, gravity hands you the exact same ticket for the ride. You might be thinking, this is all very poetic, but does it actually matter for my life down here on Earth? The answer is a resounding yes. Understanding that all objects fall at the same rate in a vacuum is not just a party trick for astronauts. It is the foundation of modern aerospace engineering and deep space exploration. Take, for example, NASA's Zero-G research facility in Ohio. It is essentially a massive 145-meter deep steel vacuum chamber encased in a concrete shaft. Why did they spend millions of dollars to build a giant hole? To drop things. Scientists drop sophisticated experiment packages down this giant shaft to experience roughly 5 seconds of pure, high-quality microgravity. In those precious 5 seconds, they can study physical phenomena that are impossible to observe on the ground. Imagine trying to design a fuel tank for a rocket. On Earth, gravity pulls the liquid fuel to the bottom of the tank. But in space, while the ship is in free fall, the fuel behaves like a chaotic, floating blob. How do you ensure the pump stays submerged in fuel so the engine doesn't explode? By dropping models in a vacuum chamber, engineers can watch the fuel behave exactly as it would in orbit, allowing them to build the systems that will eventually take humans to Mars. But there is an even more surprising, everyday application that dates back centuries: the shot tower. Before modern manufacturing, making perfectly round lead pellets for tools or firearms was incredibly difficult. Then, a dreamer named William Watts realized the power of free fall. He built high towers where molten lead was poured through a sieve at the top. As the liquid droplets fell several stories, surface tension naturally pulled them into perfect spheres. Because they were in free fall, there was no bottom pressure to flatten them into pancakes. They solidified into perfect balls before hitting a tank of water at the base. Today, we are pushing this concept even further with space manufacturing. There are certain metal alloys, fiber optic cables, and even human tissues that cannot be created correctly on Earth because gravity causes the heavier components to settle at the bottom. By utilizing the hammer and feather physics on the International Space Station, where everything is in a state of permanent freefall, we can manufacture materials that are exponentially stronger and more efficient than anything made on a planet. Perhaps the most famous practical application is the Vomit Comet, the specialized aircraft used to train astronauts. By flying in a specific parabolic arc, the plane essentially falls out of the sky at the same rate as the passengers inside. For those few seconds, you aren't just learning about physics, you are living it. You are the feather, and the plane is the hammer. Both falling together in a beautiful, weightless dance that proves, once and for all, that gravity has no favorites. So the next time you drop your keys, or that tragic cup of coffee, do not just see a clumsy mistake. See the invisible geometry of the universe at work. See the majestic, unyielding rule that connects a falling feather in a vacuum chamber to the grand orbit of the most distant galaxies. The universe is full of these magnificent illusions, waiting for us to strip away the noise and discover the elegant truths hiding underneath. Keep questioning the world around you, because science is not just equations, it is the ultimate adventure. If you enjoyed this journey into the void, make sure to hit that subscribe button and join our cosmic expedition. Next time, we are diving into the bizarre quantum realm to ask, can an object truly exist in two places at once? Until then, stay curious, keep exploring, and I will see you in the next video.